Good morning and welcome to today's Electronic Design webcast. Our topic today, Industrial Automation's Evolution to Digital Manufacturing, sponsored by TTI and Molex. I'm Bill Wong, Senior Content Director with Endeavor's Design and Engineering Group. To begin, let me explain how you can participate in today's presentation. First of all, if you have any technical difficulties during today's session, simply hit F5 to refresh your webcast console. If you need assistance solving common issues, please click on the yellow help icon below the slides. This webinar interface allows you to resize the presentation by clicking on the maximize icon or by dragging the lower right corner to enlarge the window. Additionally, we welcome your questions during today's event. We will answer as many questions as possible during the Q&A session that will follow the main presentation, but please feel free to send in your questions at any time. To do so, simply type your questions into the question window on the side of your screen and hit the submit button. Also, please be aware that today's session is being recorded and will be available on the Electronic Design website within the next week. You'll be notified by email when the archive is available. Now let's meet today's speaker. Dean Donnelly is Global Business Development Manager at Molex. He has been involved in the evolution of industrial robotic and control systems in industrial networks and integrated functional safety for more than 25 years. Dean is helping to define needs and transitions in the fourth industrial revolution. You can learn more about our speaker by clicking on the blue speaker bio widget on your console toolbar. Now let me turn things over to our presenter. Dean, the floor is yours.
Thank you very much for that introduction. First off, I'd like to say thank you very much for allowing me to be here today, and I'm very excited to talk about some of the trends that are occurring within industrial automation's evolution to digital manufacturing. Molex IAS 4.0 Complete Solutions for an Emerging Cloud-to-Sensor Solution is a number of different areas of topic and discussion that we'll roll through today, which defines that transition and that occurrence that's happening within Industry 4.0 as a general industry standard, and then how that impacts digital manufacturing moving forward. The evolution to digital manufacturing. On this slide, I'm going to walk through from an analogy point of view and from the standpoint of trying to build some general understanding, some very high-level understanding of how that communication occurs on the plant floor, or even from enterprise down to the plant floor from a digital standpoint, and how those transitions are actually occurring and actually paralleling some of the changes that have happened in our everyday life. When we think about the telephone and how it's impact our lives, regardless of how old we are, we see some transitions that we can see trends that have occurred over time, and we like to think of that transition as kind of a level set for the transition to digital manufacturing. So if we think of the first telephones when they were introduced, we can think of from an application standpoint of the communication, the way it's managed and how it's packaged from the cabinet standpoint. So the cabinet on a plant floor where everything is established today, everything is in that particular area. And when we think of those terms, we can think about how the telephone changed. And when the telephone changed from when somebody had to make a direct connection, when you saw those young men and women making the actual connection as it relates to the number that you asked for, and making a real connection, pulling wires out and plugging them into different locations and allowing that connection to be maintained. That was a very manual set of transactions. But at the end of the day, what it allowed is for communication. It allowed for one individual to call from upstate New York to California, but through some manual connections, be able to talk to that individual in the location. As that transition in telephones changed, then we started having switches in place, and those switches just aggregated those connections and really automated those connections. And we see that from an automation perspective on a plant floor in the consolidation of wiring. So assigned addresses were defined, but without networks. So the wiring and switching started to take place, and the consolidation of wiring started to happen. And we called that an MPIS, a multi-point communication connection, where we just consolidated wiring, and we put that connection out closer to the devices, and then we allowed a very large single cable to go back to that original cabinet, consolidating those connections. And we like to think of those in terms of our analogy perspective within the digital manufacturing transition as that telephone, as we all really know it got to when it hung on the kitchen wall at either our homes growing up or perhaps at our grandfather's or grandmother's home. We start to see the real transition to digital manufacturing and that evolution as we start to think about how the cellular telephone started to change our lives. And the cellular telephone started to change our lives when it became the standard outside of being mounted in a car, and it was available and on the hip of your pocket, and you were carrying it around. But what that was just networking that mobile device, that ability to communicate to different individuals anywhere without having any wired connection to it, and having that device sitting on a network. So we can think about the parallels of a network and that transition that happened on the plant floor like a distribution block, a smart block that supported industrial protocol. And those first industrial protocols were, DeviceNet or Profibus or the like, in which we started to consolidate not only the wiring closer to the devices at hand, but we started to consolidate the communication of those messages coming from those devices back to the main cabinet via networks. But again, what we have to take into consideration is that your cellular telephone at that time was nothing more than a telephone. It had a very single use. And within the implementation that exists today, the majority of I/O blocks are very much single use, which means that they are a piece of hardware that is developed specifically for a task at hand. And so taking this analogy of the telephone and that transition to the smartphone and what we're calling smart I/O moving forward really starts to embrace exactly what digital manufacturing can be. Because from an analogy perspective, you can think about the difference between a flip phone and a smartphone. What happened at the smartphone level, and which is what we all carry today, is that we have a single piece of hardware. And that piece of hardware is no different than that flip phone from a hardware perspective. It's a PCBA. It has some specific components on it like processors and memory and a number of different pieces that are built into that PCBA. But what's really different between going from the flip phone or the networked I/O to smartphone and to smart I/O is that within your current smartphone, regardless of what that is, that device has the ability to be many, many things. Yet the hardware stays exactly the same. You purchase one piece of hardware, yet that device can be a telephone, it can be a camera, it can be a GPS, it can be a number of different devices. And so that hardware is developed in such a way that it meets the requirements of all these other requirements and capabilities. And so let's try and keep that in mind as we walk through this presentation, we walk through this open discussion about this transition within evolution to digital manufacturing. All right, moving to today's architectures and really understanding what they are and understanding how they're limited in terms of where we sit within our transitions that we're seeing on the marketplace. Architectures that exist today are very consistent with the way they've been deployed since we went from relay logic to PLC-based centric systems. So that being said, majority of architectures today on plant floor or within conveyor application or within a number of, any industrial plant-based application is very PLC-centric. They're very master-slave north-south communication, which means that that communication as it relates from, the transition from the enterprise layer through to the control layer where the PLCs sit and the field layer is very much directional. You can gather information or push information from the field layer up the control layer into the enterprise layer, or enterprise can request information via the control layer, the PLC level, or the device level, but it's very push-pull. It's not open communication as it relates to real time, or it's not real communication that's related to any decision that's other than one that's been put into the system. So it's limiting. All of the safety and versus non-safe communication at the control layer is segregated. There are two separate networks. There's a safety PLC and a non-safe PLC, and a large majority of that are separate networks that exist on the plant floor. There's very loose security, and what I mean by security is that there's an inability to access securely, complex devices like robots, for example, or complex CNC machines or complex vision systems to pull data or to do firmware updates or to do bug fixes on the product via a web-based connection. And that's because of this very loose security and the fear of allowing access to a field level device and allowing that access to perhaps then migrate and make its way back into the enterprise layer where companies can be hacked. And so those security measures are starting to be put into place, but in general, they're quite loose. There's very little machine to machine, and what I mean by machine to machine is the ability for two complex machines, like two robots, to make decision based on occurrences that happen within the manufacturing level without being tasked to do so specifically by the control layer. And there's very little remote access. Very little complex machines have direct Ethernet connections with secure connection that allow for maintenance updates, that allow for polling from a configuration standpoint or firmware updates or the like. And what does that mean moving forward? Like, how do these limitations that exist that have just been, because of the way the transitions have occurred in the market, how do those have to change? I like to point to the analogy of the flip phone versus the smartphone, and flexibility is a big piece of it. A big chunk of that is also emerging business models. Everything is a service, which means that the way in which complex machines will service their products at the field level moving forward might not be to implant a engineer within a facility based on that facility specifying a number of their complex machines, for example. It may mean that there is a defined safe connection that is has secure connection on it, that is in place, where then the support and the maintenance and all of the interaction between the manufacturer and supporter of that complex machine does all that business remotely. And that then is, from a business model standpoint, that changes everything the way that company manages their equipment. And therefore, that can build cost out of the application because they're not inserting an individual, for example, directly on site. And so that builds cost efficiencies. And that builds the efficiencies as it relates to, travel, as it relates to all those different pieces. So that's just an example of some of the things that we see changing moving forward. So when we think about these limitations that exist today that we all know about, and this drive to Industry 4.0 is very specific around an understanding of some of these limitations and the fact that a number of these emerging technologies will allow to build these efficiencies in. So what do tomorrow's possibilities bring within IoT and Industry 4.0? And these are defined within the program that we're working on, is that Molex Industrial Automation Solutions 4.0. It really creates something that's much more open, where you have, a much more distributed control strategy, where you no longer have just communication that's master-slave. So, for example, flip phone to flip phone, or flip phone to home phone. You also have the ability to manage multiple connections between multiple devices at the same time. Each one of these devices has the ability to take on other responsibilities. So there's embedded support for safety and integrated security. There's no real differentiation between IT and OT. It's one technology. IT is information technology, which is IT that we know in our day-to-day lives. OT is operational technology, and that's the management of the devices at the field layer, the sensors and the complex scanners and devices, and the ability to have all those devices as we move forward have more intelligence and be able to intercommunicate and make decisions that are best for the manufacturing process or best for the organization's long-term goals and strategies. Each device having embedded security, so you know that when you speak to a device or you make a connection to a device or you make a connection to an area of ownership that you have, you know it's secure. And from a security standpoint, I like pointing to online banking. I can recall when online banking first came on, there was so many people that were, I will never do my banking online. It's not safe, and it's not secure, and you can't trust it. And there's very few people today that don't do the majority of their banking on their smartphone. And so the safeguards that were put in place and the proof that was provided in order to get us to the level that we trust that connection. Those are the same types of things that are going to happen within these transitions to what we call tomorrow's possibilities. The ability to have real-time machine-to-machine and to have remote access from anywhere. And that remote access is very, very important because it allows for offline configuration of devices and such that just are going to change the environment in which we live. Competitive advantages. So what makes Molex and our collaboration partner TTI someone you want to talk to with regard to transitions that are happening in this area within Industry 4.0, within that transition to digital manufacturing. Basically, we are recognized as an industrial communication competence center. Within our core IP, intellectual property, we support a large array of field bus communication protocols for safe and non-safe, for scanner and adapter that are all TUV certified. We are one of the leaders that in the market and have been for a very long time as it relates to standard industrial protocol for Ethernet IP, for Profibus, Profinet. We've developed backplane modules that sit on the backplane of, the majority of communication and PLC manufacturing collaborations, across the globe in all flavors. That includes Ethernet IP, Profinet, Profibus, TC-Link IE, DeviceNet, Remote I/O, TC-Link IE, EtherCAT, and for master-slave, scanner and adapter, safe and non-safe. We design and manufacture our own industrial protocol stacks and hardware solutions. That's very important because as we move towards this next transition in the marketplace of digital manufacturing, the ownership of that IP and the ability to implement those pieces of technology, not only on the hardware platforms or not only on the solutions that we provide, but also as we work with collaborative companies that require pieces of it that can then sit on that more distributed control architecture that we just walked through, that have the ability to pop onto that architecture and then intercommunicate with multiple devices manufactured by multiple manufacturers supporting the same communication methods. The fact that we design and manufacture on our own brings a lot of credibility to our program. So from conception, from a design standpoint, the intellectual property and the manufacturing of the hardware from a capability standpoint is something that's all owned in-house. 23 different manufacturing facilities. We have within the development of these digital manufacturing technologies from a deployment standpoint are developed in 3 different engineering areas, one in Waterloo, Ontario, Canada, the other in Cartebec, France, and the third is in India. So we have all of the supportive structure from a software, firmware, and hardware, from a development, from a deployment, and a manufacturing standpoint. We offer the solutions in a fully integrated modules for integration or defined deliverables. So what that means is that we understand the importance of this transition of digital manufacturing. We understand the importance of supporting multiple protocols from an industrial standpoint. And that means that we're going to be sharing pieces of this with other manufacturers. We're going to be sharing pieces of this with multiple device manufacturers of products moving forward. As an analogy I like to use, from a Molex perspective, we have been, to some degree, the Intel inside from protocol communication within the industry. Multiple manufacturers of multiple products have used these pieces of our technology to allow their products to intercommunicate as scanner and adapter for years and years and years. The difference now is that we're trying to transition and trying to build more value proposition to drive to a more complete solution of distributed control. So where really has been the role of us in factory automation? Going to my last point, we've always been enabling devices with protocol capabilities, as well as mechanical connections for power and device. So of all the different technologies that I mentioned, including some of the up-and-comers like IO-Link, we support the technology not only at a technology level, but we also support it at a product level, and then with our collaborators, we provide it within solutions that are offered even from a sensor perspective we can move to. So it's really about, on the plant floor, having the role of making connection from a communication standpoint. And if that connection rolls from where the asset, the device, is connected from the PLC to the distributed I/O, and from the I/O via that media to the sensor, and then also the support of the actual protocol and communication that is required in order to make that communication possible from a packet level. So the communication packet itself. The evolution of digital manufacturing. So moving forward, we understand that to some degree there's going to be no difference between a safe and a non-safe device at some point in the marketplace. So moving forward, hardware must be developed and support TÜV certification. Connectivity has to be there from both a physical media standpoint, what I mean is the cable, and from a communication standpoint that supports the rules and it supports all of the standards that exist within the protocol, regardless of what that is, whether it's, for example, Ethernet IP or Profinet, or SIP safety or ProfiSafe. Each device, moving forward, we feel, will start to have logic embedded in that. So we'll have some decision-making capabilities. We think that in the short term, that logic will be limited to some degree, and there'll start to be islands of automation where you can distribute some logic and then tie, basically just a connection to perhaps in the short term a supervisory PLC, but then offload perhaps some safety logic within application within your systems infrastructure and within your architecture. IIoT is a big piece. So when we talk about IIoT, we really talk about the connection of the product via the cloud or via an on-prem server, and having the ability to have all devices connected securely, like that smartphone that we talk about as an analogy. Supporting within the program, supporting pre-certified or custom developed apps. What does that mean? Again, I'm going to point to the smartphone. and the way in which you use it. We all know, and we've all used the application store where we've gone and downloaded a very specific application that allows us to, have perhaps a much more completely defined performance-oriented GPS, or turn our phone into a level because we're hanging some pictures in the living room. Think of it in those terms where all of the hardware, like your smartphone, has the capability of managing all these different pieces that you have access via the app. So imagine you have a hardware platform that is functional safety rated. It's secure hardware platforms that can be delivered in different form factors. So you can think of it as an I/O block where it's distributed from an IP67 standpoint, or you can think of it, for example, as a PCBA that supports PCIe as an electrical interface and is put into a PC-based controller for a complex machine. But what that hardware needs to be able to support is all of those connectivities. That hardware must support major industrial network technologies for standard and safety communications, as well as machine-to-machine and wireless communication moving forward. That hardware needs to support development and execution of standard or safety control application and be able to act as the brain of the machine. It has to be able to support IoT. It has to be able to support some cloud connection for connectivity. If with filtering and aggregation of features, what we mean by that is, in the future, if you have a piece of hardware that might be like an I/O block that's mounted on your machine, and that I/O block fails, right now, the way we're looking at the market, you might have to have inventory of that specific block on the shelf. You'll have to pull that specific block, and then you'll have to configure it in the same manner to replace the damaged device that's on your machine. Moving forward within the transition to digital manufacturing, we very much see in the future where, it wasn't that long ago I didn't lose. I broke my telephone when I happened to be on a business trip overseas. It was unresponsive. I didn't panic. I finished my day. At the end of the day, went to an Apple store. It happened to be an Apple phone. I purchased a telephone. I took my SIM card out of my broken phone. I put it into the new Apple phone. I got a Wi-Fi connection at the hotel. And within 10 minutes, the device in which I had broken, with all my pictures of my family and all the different apps, the way I like them loaded, and all the different configurations that I'd created for that product was back. And it was very, very convenient. It was easy to use. And so we see moving forward that cloud connection being very important in terms of a standard hardware platform, so that everything as a business changes. You don't have to have as many devices that you inventory from an MRO standpoint. You don't have to support, a very long list of components, because if that one device supports, multiple personalities, it could be different things, and you can onboard it that quickly, then there's a business model there, there's cost saving, there's a number of different advantages. And then there's the ability for customer applications, for the ability to write your own application. That might be for an algorithm that has to do with some motion, for example. It might be with some data mining that you want to do. But you're going to want to, in the future, be able to very much customize your solutions in order to have the personality that's needed moving forward based on your requirements and application. Applications of distributed control are very simple. In an application where you might have a small cell that might look like this, you may include, a device like a network interface card. But that network interface card sits in a PC-based control platform for a complex machine like a robot or a CNC machine. There's multiple different examples. Any PC-based control, any complex machine that has its own control platform. You can then include industrial protocols, so allow it to be a master and slave on whatever protocol that you need based on where you're selling the product from a logistical standpoint, because some languages are different in different areas of the world. You may include the ability to support some control. So you want to do some I/O support and maybe have some logic running on there. So really having one common interface for multiple protocols and standards can be implemented through a small exchange of requirement specifications. Or an application more like conveyor application or more like line builder application, you can actually package it in the form of an I/O block that supports I/O and distributed logic, includes I/O sensing, embed safety and logic and control capabilities for customers to add control functionality and optimize the application. So it really is a transition that is going to, we feel, happen over a period of time, and those timelines are being defined as we talk today. But from an application view, it really translates to an application where, for example, you might have less supervisory control. So what that means is you might have a number of these blocks from a conveyor application, and you might have the block in the lower left that's configured as a master, and then it is supporting the connection to each of the other blocks that is configured or given a personality as a slave only. And so you have the flexibility to really architect your system based on what you use. And because the devices are only applied based on the way they're configured, you're only using the pieces of technology or you're only paying for or using the pieces of technology that are specific to your areas of ownership or your areas of need from an application or architecture standpoint. All of those common aspects are associated that we walk through: the ability to make cloud connection, the integrated security, and the ability to allow, as I mentioned when I lost my telephone, onboarding of the device or the maintenance of a digital twin of that particular device and being maintained on a cloud someplace. So if someday the product fails or you need to just monitor the system offline, that can all be handled securely, remotely. So it's really about transitioning control to the point where it's less rigid and it's a lot more open. That's really the key that we're seeing in general from a trend standpoint within Industry 4.0, and that we're trying to deploy in the development of our IAS 4.0 program. Digital manufacturing will depend on multiple industrial networking technologies, delivering real-time information, intelligent sensors, and being on the edge of operations to enterprise and beyond. So that we encapsulated through this entire piece, but that means that working with partners from an asset standpoint, from a sensor standpoint, that enable themselves with some of the key technologies, for example, being able to support safety, to having a secure connection built in from that standpoint, and being able to sit on a very open network, to be able to support multiple protocols just by clicking off the protocol you want to use versus having to buy a separate hardware platform. These are all part of those transitions that we're seeing in digital manufacturing, and these are all part of the interactions that we're having through consortiums, through different working groups, and through working within to some degree even competitive suppliers of solutions, in order to create a world where everything can talk to everything else, and that's going to take some real consolidation of agreement on technology and deployment of those technologies and specifications around those technologies. And so how do we unlock the full potential of Industry 4.0? That's a question that, since Industry 4.0 as an acronym, as a buzzword first came out, it's really interesting because, for myself personally, when I thought about Industry 4.0, when it was first starting to become this buzzword out there within industrial automation, it meant so many different things to so many different people. It depended on, how they viewed it. And I think taking a very holistic view is what we need to do moving forward, is that we have to look at it as the consolidation of communication. So today we speak multiple languages. We have to support multiple languages from a protocol standpoint, depending on where products are being deployed and depending on where a specific technology might have its roots. Moving forward, like the business world, if you attend a meeting in Germany or if you attend a meeting in Japan, and there's people representing multiple countries, it's becoming more and more common today that those meetings are held in English. And because we have to have a standard foundation in order to understand each other. And we see that the same way, is that, yes, there will be support for multiple protocols for some time to come, but the transition really has to move to some point to support different areas. So OPC UA is very important. MQTT is very important. And TSN, time-sensitive networks moving, are very important. So, you know, from a knowledge share standpoint, or from a trying to provoke discussion, we really see, you know, the need to be to some degree, you know, protocol agnostic or to be language agnostic from a control standpoint. And we need to get to the point where, regardless of what sensor you buy or what piece of automation equipment you buy, the ability for those devices to intercommunicate is either defined, or there's an ability for the manufacturer or provider of that product to enable that capability. And that's when the market really opens up, and that's where we start to see those efficiencies from a cost and a deployment standpoint really start to take effect. The role of connectivity. So the role of connectivity, where we sit today and the role that we play, and working with our collaboration partner, TTI, what are the areas in which Molex and TTI can help you today moving forward? You know, from a connectivity standpoint, plug-and-play technology, IP67 or higher design within our I/O blocks. These are all governed by international and local electrical and safety standards, and the support for all common industrial wiring requirements: I/O single, control, communication, and motor power. There are solutions that exist within the Molex portfolio that are offered by TTI that can fulfill all of those requirements, and we highly encourage you to reach out to the teams regarding these areas. The first area, I want to roll through it just real quick because it's very important that you understand what we offer today. Control power. The power that, Brad power, the ability to make quick connection via our 7/8 mini change, heavy-duty multi-pin connectors, M12 and M23, are all products and solutions that are inventoried and that are available, and many different form factors in many different, you know, lengths or custom lengths that you can use within your control power applications. Signal. A complete line of M12, heavy-duty connectors, M8, and DIN connectors, regardless if you're talking about your hydraulic and pneumatic valves or your proximity sensors or photoelectrics. The ability to make connection physically to those devices at that level, at the device level, those solutions are a big part of our portfolio, as well as network communication. The ability to make connection to devices regardless of what network they support, whether that be Profibus or Ethernet IP or DeviceNet or serial for that matter. A complete line of M12 decoded and Cat5e solutions, heavy-duty connectors, M12X coded, as well as RJ45 for connection to in-cabinet or to connection to that enterprise layer. Motor power, the connection to bring Brad power, M35 connections or heavy-duty connections to, or M40 connections to those motors that you actually have sitting down along your conveyor. We have quick connect solutions in multiple different areas that in many ways are leaders in the area of technology for many, many years. As well as a line of products offered by and within collaboration with Contronex for inductive and proximity sensors that support, you know, technologies that support IP67, that are vibration and shock resistant, and also support IO-Link as a technology moving forward, which we feel is a big part of that transition. In collaboration with TTI, Molex provides that real common thread that allows the interconnectivity from the edge devices, so from sensors to the enterprise via copper, fiber, and wireless mediums. So bring out these world-class brands together under this collaborative roof, TTI and Molex. We really feel that we bring a very strong position as it relates to that interconnected world that exists at the field, device, and enterprise layer. In summary, learn how TTI can help guide you with Molex connectors, sensors, and cables. I'd just like to thank everyone very much for the time today. And I'd like to take the opportunity right now to move to any questions that might be on the back of your mind or in the front of your mind. I'm open to any of them. Thank you so much for your time.
Great. A few of you have already submitted questions, so we're going to jump right in. If you'd like to submit a question, type your question into the question window on the side of your screen and hit the submit button. While we're answering your questions, please complete the feedback form, which is located at the bottom of your screen. So to start with, Dean, how will 5G wireless communication impact traditional wire communication, like Profibus /net, IO-Link on the factory floor?
That's a great question. It's one that that's in discussion, at very many levels. So what we're talking about here is just that, is factory floor. What we're seeing right now is really the ability to from a technology standpoint to securely and reliably use 5G for replacement of wired communication on a factory floor. The technology is there; it's capable. What we see is that just within transition, within factory automation, there are a number of criteria that really slow down the transition from a technology perspective, and that's legacy-based control systems, support infrastructures for those control systems. It's just that it's such a defined position that has been created over a long period of time. Transitions from even hardwired to networked, and then networked to including functional safety. We're seeing those. They're very incremental in terms of adoption. Now technologies like 5G and the way that the market and the way that the available the capabilities within technologies is being defined is there. It's capable, but we see a large problem with regulatory. So I think if there were no restrictions on having and everybody was committed to drive forward to full wireless, and there was regulatory requirements were lifted, and you could have you could very easily have your own network, so private network, to manage all of communication and firewall that between enterprise and device and level. It's there, but I think our position right now is that it's going to happen in phases. So there will be places where different pieces of technology will be deployed based on segregation and the ability to manage that implementation. If that answers your question, but it's not a limitation on technology. It's regulatory in our mind.
I think that did it. You mentioned every bus but CAN. What's the future of CAN?
Well, from our perspective, what we really have within our early adopters and within our development process around the IAS 4.0 initiative, it's not that CAN is not on our roadmap. In fact, we have internally, the ability to support CAN-based networks. We've developed CAN products in the past. So it's not about the protocol. It's not about the implementation. It's really about priority, and it's really about where we've got, our feet in the sand today with respect to true early adopters and defining implementation around protocols for safe and unsafe, including logic within specific opportunity. CAN is not off the table. It just, from a priority standpoint, is pushed back, but that can change with discussion around opportunity or a specific project or such. So I'd be very happy to engage with someone that would be interested in pursuing a project based around CAN and defining those requirements.
Okay. What is the timing behind the adoption of full distributed control?
Wow. There's so many dependents on that timing. We like to look at, I was around, when really networks were, well, it's sad to say, but I was around actually when we went from click-clack, from relay to PLC, and when we started to adopt, networks as standard fare on the plant floor. And it really depends on the willingness of systems architect owners to make that change. And it really has to do also with the after-sales support and the infrastructure for support of systems that are deployed within industrial application. So what we see happening is phases of it, occurring. So as we saw, the transition from, let's just say, for example, from DeviceNet to Ethernet IP, that transition took a period of time to happen. As functional safe-based, solutions became available, then the transition to those, to managing safe-based communication on the same wire. We're still in that transition right now. So what we see from our early adopters is that there's pieces that are going to be implemented, over the next year, 2 years, 3 years. And what we see is as far as our crystal ball looks today, and based on our early adopters of the technology, we see anywhere between 7 and 10 years for full implementation of what we're defining as being a much more open architecture, let's call it, right? So distributed control, where we get to the point where, I mentioned in our strategy around hardware is the strategy that all hardware is, safety certified, PE certified. So to deploy new pieces of implementation around those technologies, it's not about, the redesign of a hardware platform. It's back to that analogy we were on the smartphone, where you have one hardware reference platform that then can be turned and twisted and certified very quickly. So yeah, we see that timing coming in pieces, but we think that it's going to be in the, really from a, if you look at basic, network implementations, seeing that timing, in that phase, in that 5 to 15 years, with pieces of those technologies being implemented along that journey.
Okay. What is the adoption rate of integrated functional safety?
Well, that's what I was just pointing to. Is so we still, when we talk about integrated functional safety, from our perspective, we talk about not having to plug a device into a third-party product to connect to the safety to a separate safety network. We see the ability of each, of a complex device, even something like a safety scanner or a light curtain, having that connection built into the device, rather than having to plug that into a device that manages that connection. So we're working with complex device manufacturers right now that plan on deploying a product that has that integrated solution. If you look to the man-sized robot world, there are features for integrated DeviceNet safety, integrated adapter for SIP safety, for example, and ProfiSafe, integrated really at a software level, but then deployed and certified on a TÜV certifiable hardware platform that's been defined by our customer. So, and we're also seeing now the need for, master capability or controller-based capability because of a complex device having the ability to have some of their own I/O supported, and being able to, for example, be a master or a controller to their own I/O or their own cell, yet be a slave to some supervisory. And so it's started, if that helps to answer your question.
Okay. Where are the main barriers in technology adoption?
Legacy infrastructure. Some of the barriers, and there's some fears out there as well. If we look at fully deploying a distributed control platform of hardware that supports safe and non-safe, either controller or adapter capabilities for whatever protocol, there would be a support mechanism associated with that. So, having maintenance, be very familiar with it, have an ability to make a secure connection via a internet connection to a device, and if that device is sitting on, the plant network, and that plant network is firewalled to the enterprise, there's that fear around, or it's not so much a fear, it's how do we prove to the decision and the decision maker that there's no chance for that device to be hacked, and there's no chance for that device to be, to allow, some portal up to, their business systems, for example. And I think it's about education. I think it's about real open discussion around those questions. So, for example, I remember when internet banking first hit the scene, there were so many discussions with, individuals, and including myself at the time, was, I'm going to stay away from that because there's some fear from a security standpoint within that. But it's proven, like the analogy around the telephone, that can be made secure. But there's a set of measures that are put in place and it's a real business model, and it's a real development model around, putting in place those measures to create that security. So I think it's about education. I think it's about the understanding that none of these technologies that will drive to all these efficiencies on a plant floor, none of them are not available today. It's how they have to move from one medium to another, and they have to be combined and then embraced, and then a support infrastructure built around them for knowledge share.
Okay. Where are we seeing early adoption in the transition in industrial automation?
So where are we seeing the adoption? So it's in small islands. So what we're seeing is areas where there's a systems architecture in place that's Ethernet IP based. It is very PLC centric, so you have that supervisory PLC. But where we're seeing the first adoption is in areas where, for example, in a true man-sized robot location, where you have a safety celled area, where now within specifications that are coming from the larger manufacturers, they're giving what's called free expression to the robot or the cell provider to deploy within their area of ownership systems that, so long as they are able to intercommunicate seamlessly with the supervisory and the standards that relate to protocol and communication and functional safety, they are allowed to provide free expression. So they can come in and quote a system that is quite different than what would be used from a hardware and a deployment standpoint if they were just to buy, the existing system. So, they can have safe and non-safe messaging running through a single device so long as they're managing that in using the same technologies, and so long as they support that cell once deployed in the manufacturing facility. So we're seeing it where there are areas of ownership and free expression from a specification standpoint. The key to that is the ability for these devices that might be able to support, safe and non-safe, it might be configurable, it might be able to be, provisioned or onboarded as multiple types of devices, as long as that can intercommunicate and sit with and be configured within the software systems that are deployed for the overranking specification on the control architecture. That's where we're seeing it. And then we're also seeing it embedded directly into complex devices that may have, PC-based, they may be a PC-based control platform. They may already have TV certification or not have TV certification. And so a third-party device is specified for them that allows them to be a scanner and or adapter for safe or non-safe protocol support.
Okay. Do you see any synergy between automotive and industrial? For example, automobiles are becoming more like industrial machines.
Yeah, that's a fun thought process, So, yeah, I do. So, this is kind of dreamy, but this is kind of a thought leadership or not so much of a where we see things going in the future, and there's timing associated with the deployments, but it's really interesting to me when you think about in 2014 the average automobile had like 2 or 3 CPUs. I was just reading the other night, because I'm kind of a car guy. I was reading the other night this new all-electric Volkswagen that is being released. It has 87 CPUs in it. And if you look at really if you look at Industry 4.0, what it really is the consolidation of hardware and the bringing together of technologies to reduce the overall cost of, factory control-based systems, and then to build in, remote connection to get to that point where we have lights out. One of the interesting discussions that's happening from a robotic standpoint is that, the assembly line, the Henry Ford assembly line that has been, the de facto standard from a car manufacturing perspective for a very long time, it's going to slowly disappear, where rather than the vehicle sitting on this assembly line and then moving to the areas of automation, to the robot cell, to the spot weld, to paint, where we're going to start seeing trends where the robots will move around. So much more flexible capability from a manufacturing standpoint is starting to take hold in terms of a next step from an automotive plant. So when you think about the infotainment system that is in most of the new cars today that go out, so that infotainment system has the processing power and has as much processing power as, say, for example, the control systems that are building the car today in the plant. So you have to ask yourself a question long term, if that's going to continue and automotive manufacturing truly embraced Industry 4.0, well, couldn't you load all of your code and all of the manufacturing parameters, including all the build case for that particular vehicle, into the infotainment system, for example, and deploy that manufacture of that vehicle based on that controller managing the build cycle? And then, when the car is finished being manufactured, then the infotainment system gets flashed to an infotainment system. So it's very interesting to think that the capabilities that are available from a technology and control perspective, they're built into the vehicles already. So I see a lot of similarities between the automobile and the plant floor, because when you really look at an automobile, if you look at the way it's wired and how CAN is used for the oxygen sensors and for your tire pressure and for all of that piece, that if you took a vehicle and you just broke it out and you laid it out on a plant, it is a plant floor. It's doing the exact same thing. So yeah, those parallels are very interesting to think about, and that's part of that long-term thought of where we are going to really get within Industry 4.0 and what that really means in terms of the consolidation of hardware, because it's really what we see is that consolidation of hardware. Back to that analogy, I don't have a GPS stuck to the windshield of my car anymore. I really barely use the one that's in the infotainment system. pretty much use my phone all the time. I don't carry around a digital camera. I don't have, my Texas Instrument. I don't. All of that capability is built into the hardware. So how that transitions, that's a very long discussion, but very interesting one.
Okay. Is connectivity feasible on older platforms like GSM 2G wireless mobile networks or old Wi-Fi setups?
Is connectivity feasible on a GSM 2G? You mean connectivity from the perspective to support, let's say an industrial-based packet being transitioned over that network? Is that what we mean?
I think that's the case. They're trying to figure out whether or not they can make use of an existing infrastructure.
I would say no. I would say that wouldn't be the way to do it, and it's really around the security piece. But I'd be more than willing to have like a discussion with the individual that posed the question. No problem at all.
Okay. Well, I'm afraid we've run out of time. For those questions we didn't get to, we'll be getting back to you via email. This concludes today's presentation, and on behalf of Electronic Design, I'd like to thank TTI and Molex for sponsoring today's event. Of course, to all of you for joining us. Have a great rest of the day.